Okay, guys, these are my questions that I had to do for our homework. I'm including both my chapter 1 questions and my chapter 2 questions. So the first problem that I had to do is question 1.2 on our homework. It reads, with reference to exercise 1.1, verify that if n2I equals the constant n sub 2, the formula obtained in part A reduces to that of formula 1.1. Okay, so here's my 1.1, the problem that it references, and here's what I had my tree diagram look like. The formula that I came up with is the sum from 1 to n of I of n sub 2i. So that means I'm going to have n sub 2i ni times. So I rewrote that here using n sub 2 as my constant because that's what it says in the problem. And I know that n sub 2 is a constant, so I'm pretty sure it's going to be n sub 1 times n sub 2. But what in talking with some of the other girls, what I decided to do is give myself an example. So if I used 3 as my constant and I wanted to have it 5 times, then I would have from 1 to 5 the sum from 1 to 5 of 3. So I will have 3 5 times. So 3 plus 3 plus 3 plus 3 plus 3, and that equals 15. And if I use the formula n sub 1 times n sub 2, that would give me 3 times 5, and those two are equal. So I think that is the correct answer for number 2. Okay. The next problem that I had to do was problem number 1.43. How many permutations are there? Sorry about that. How many permutations are there of the letters in the word great? So the first way I thought to do it was give myself 5 blanks. In the first blanks, there's 5 possible letters to choose from. And if I choose that letter for the first blank, I don't have it to choose for the second blank. So that gives me 4 possible choices, and so on. 3 possible, 2 possible, 1 possible, which gives me 120. Using the formula from the book, 5 factorial, I have 5 different times to choose 1 letter per time. So that would be 1 factorial. When I simplify that, 5 factorial, that equals 120, and those are the same. The B part of problem 1.43 was, what if the word was greet? This is slightly different because I still have, I only have 4 letters to choose from. Even though there's 5 possible letters, I have 2 letters that are the same. So I only have 4 letters to choose from, 4 times 3 times 2 times 1, which is 60. Using the formula that was in the book, 5 factorial, because I'm actually starting with 5 letters, but this time I have 1 choice for the G, 1 choice for the R. I have 2 choices for the E's because there's 2 E's, and then I have 1 choice for the T. So when I simplify 5 factorial divided by 2 factorial, I end up with 60. Okay? And my last problem that I had to do was in chapter 2. Almost there. My last problem that I had to do was in chapter 2, and it was problem number 2.19. So it says duplicating the method of the proof in theorem 2.10 show that, and I'm sorry, Dr. Davis, but I don't really know how to read all these, so I'm just going to do my best. Prove that the probability of A intersect B intersect C intersect D equals the probability of A times the probability of B choose A times the probability of C choose A intersect B times the probability of D choose A intersect B intersect C, provided that probability of A intersect B intersect C is not equal to 0. So I looked in my textbook for the proof to problem 210, which is right here, and I noticed that we already have the value, because of the proof, we already know that A intersect B intersect C has this value right down here. So I used that in my proof. I said, first of all, we can separate this to be A intersect B intersect C times P, the probability of D choose A intersect B intersect C, because that's the same pattern that it was in proof 2.10. Using what was in 2.10. By theorem 2.10, I know that probability of A intersect B intersect C is that. So I just used what was in the textbook here, and then I had already separated out the probability of D choose A intersect B intersect C. So that is my proof of that statement right there, which is problem number 219. Thank you very much. Have a great day.